right, welcome back, guys.
Nice haircut, Mr. Holloway.
Thanks. It's a low taper fade. Bet. Cool. All right, so 4.2. That's worth at least 2 booms, yeah?
Three booms. 3 big booms.
Gosh, I'm cool. All right, we are looking today, 4.2, we're going to start. We're going to be looking at types of waves. So I just passed back all those quizzes that we took the other day. Hopefully that was not a traumatic experience for you to go through. We looked at waves the other day. What are the three main things that make waves in our ocean? Wind.
Storm.
Storms are wind, I would argue. Earthquakes and landslides. Now, they make different types of waves, right? A little bit of wind with a little bit of room to blow, or fetch is what we call that, makes essentially ripples. You let wind blow strong enough and hard enough over a long enough distance, and you're going to start getting bigger waves. The only other part of that first section that seems odd is when we talk about progressive waves. When I think progressive, I think continue to grow. That's what I think of progress. That is not what is referred to as progressive waves. When we have wind waves or whatever they are that turn into progressive waves, when we say that word, they keep progressing in the direction that they're going. They don't keep growing and getting bigger. Normally they get smaller and more smooth and become swells. But that progress part of progressive, they keep moving. That's all that it's indicating. Now, we know how waves get made, at least at a basic level. We're looking at types of waves. We're only talking about oceans and large bodies of water in here, just so that we're all on the same page. The ocean, there's a lot of ocean. Obviously, it's like 70% of our planet. But there's really only 2 broad categories for which waves can exist. They can either exist in really deep water, right? Certainly there's waves in the middle of the ocean, above the Marianas Trench and all that. But waves can also happen where? In the shallows, yeah? I think that's what you said. Cool. Now, looking at these, we are going to look at those 2 types and some of their characteristics and see that maybe there's a little bit of gray area between them. But to start off types of waves, let's just start in the deep sea. So we're going to look at deep water waves. Now, there's a natural question, I think, that kind of lines up with this. What is deep water? In your mind, just take a shot in the dark. How deep is deep water?
Pretty deep.
Can you give me a number? 7 feet's pretty deep? Maybe. 3 meters, so 10 feet we'll call it. Is that pretty deep? So 200 feet is starting to feel a little bit deeper, I think. But is anybody wrong with their answer? No, because what's deep water, from your perspective, probably depends on how long you can hold your breath, how deep you can swim, and all sorts of those things. Somebody who scuba dives probably won't say 7 feet is very deep. Somebody who can't swim is going to say 7 feet is super deep, and they're not going to get in, right? Like, there's different context there. So when we're talking about these, we have a formal definition that takes all the ambiguity or I want to say unclarity, but that's not a word. Nebulousness out of it. So deep water waves, shocker, but they travel through deep water. But I'm not going to write that because that's redundant. They travel through water whose depth, and I have a suggestion right off the bat. We're going to write depth about 50 times today, unless we just agree that a lowercase d represents depth. Let's use lowercase d for depth. You can write it if you want to, whose depth, d, is less than or equal, or sorry, we're talking deep water, my bad. Greater than, we need the depth of the water to be greater than 1/2 of the wavelength. Okay, whether or not water is deep with regard to a wave depends on how is the wavelength between them. Okay, by definition. Now, this is going to be used and referenced again. We'll see it again, so don't stress about it. Mathematically, I think most people in here can probably do this, but we should check. I have the following, and I don't care if you draw this or not. With all things notes, I'm going to require that it looks like you're kind of writing stuff. You do not have to write word for word what I write. If it'll help you, like, stop you from falling asleep or something, please do. Like, take advantage of that. But let's say we have the following waves. They're nice. And I take this point here, and I measure it to this point here. How big is that distance? Don't care. Make up a number.
150.
150 what?
Feet.
150 feet. Okay, I'm going to make the claim that this is a deep water wave. Okay, at least how deep for this to be a deep water wave? Okay, that's a question at hand. There's obviously not a math class, but between you and your neighbors, some of you are going to be able to do this in your head, some of you are going to struggle. Your job in here while we're doing this is, if you're one of the people who can do it in your head and you understand it, no issues, it is your job to help your neighbors understand. Not just give the answers, but understand. If, hypothetically, Leanne just can't get it and Keisha explains it 3 different ways and Leanne's going, I don't know what the hell you're talking about, who could she ask? Yeah, probably this guy up here or somebody else if you guys would rather. I want to know, if this is a deep water wave, how deep is the water that this wave travels through? Looking at it, I'm going to make a little change and I'll highlight it in a different color so it's really clear that I made this change. Huggins brought up a good point because he heard the answer that I discussed with another group and he said, isn't it this? I could have countered back at you, but this will just take out all the issues there. I'm going to say or equal to. We'll just use that. Because somebody said, what do you guys get just out of curiosity?
With that, with greater than or equal to,
Sure.
300 more.
Why?
Because it has to be greater than.
Okay,
No.
I see your logic, but we're going to do one little thing real quick. What is the wavelength of this wave? Okay, so you do not have to use this. Lambda is a symbol we typically use for wavelength. Cool. Wavelength is 150. Everybody good with that? Okay, so deep water waves travel in water whose depth is at least half the wavelength. So real quickly underneath, and again, not a math class, but I just want to make sure this clicks for everybody. What's half of 150? Which means the depth of the water that we're traveling through must be greater than or equal to what? 75 feet. Yep, you went the opposite way. It makes sense. It's easy to do. You're probably doing some fraction busting along the way. Easy to fix, easy to make. Now, before I added the or equals to, when I answered 75, somebody said, shouldn't it be 76? And just to be a little bit snarky, do you guys know what snark means? I know how to use it and what it represents, but I don't know that I can define it. Like, snarky is like a smart mouth, right?
I thought snarky was like someone who's just like a negative.
Oh, maybe I've been misusing it my whole life. Huh. We'll do some Googling here in a minute. All right. Give me any number greater than 75. Huggins suggested 76, which makes sense because we're talking in feet. But it's 75 feet and 0.0000000000001 inch. Like, it gets infinitely close. This is just getting rid of that. Okay. So we have a deep water wave here. Now, as we move forward with this, whether I doubt I'll ask you to do this calculation. I just want to make sure that we can all think about this as it happens. Okay. Moving a little bit forward from here. Remind me real quick, if we have a wave in the ocean, they carry something specific. And there's a lot of different answers that I think would make sense. But waves, especially in the water, they carry something very specific. The natural answer that everybody, I think, probably wants to answer, and I just want you to gut feeling, everybody say this, whatever your answer is going to be. 1, 2, 3.
Energy.
That is not what I was expecting, and only like 3 people said it. What's the obvious answer that, energy is what I wanted, just so you know. Waves carry water is what I was expecting people to say. Now, why don't they carry water?
I think they do carry water.
You think so?
I think.
But we know that if there's a particle of water on top, and I can think of it like a big ping pong ball that's floating, and a wave passes through it, that particle of water, or the ping pong ball, doesn't keep going, right? That particle just does this. It's that orbital motion that we saw from that forward and backward kind of motion of a wave. Waves carry very specifically energy, not particles. Now, it doesn't really matter what the particles are. We can think of them as pieces of water, stuff floating on top. Waves carry energy, though, in this situation. Now, in physics, the same way. Waves of light carry the energy and the photons. The particles move along with it. Fundamentally different. Water behaves differently. Okay, beyond that, I'm not going to write this one again. We talked about the idea of a wave is generated and it keeps progressing in the same direction that it was going. What did we call those? So that's more roundabout. Maybe we don't need the question. We're going to define it real quick just to make sure we have it. We're going to define for ourselves, even though we might already have it, progressive wind waves. Now, because I put a lot of thought into how I outline and stuff, without going too crazy with it, where do you think progressive wind waves might be common? Deep water, shallow water? So you'll probably see them there, but they don't have a ton of weight. What section are we in? What's our overall topic that we started with? So these progressive wind waves reasonably, seemingly would happen where? In deep water. Now, can wind waves, and specifically progressive wind waves, they're just the small ones that keep traveling, could they happen in shallow water too? There's going to be overlap, right? Like it's going to happen. As we look at these, I don't know that I have to say a ton more about this, other than they keep going in the same direction. Now, in the ocean, when you get progressive wind waves, even if there's a big storm and you get, let's say, 20-foot waves, as they progress forward and they keep traveling, do they get like crazier and bumpier, or do they start to kind of mellow out? Imagine a big wave in the middle of the ocean and then the wind stops blowing. Does that wave keep getting bigger?
No.
Probably not. It realistically should get a little bit smaller. Is it going to be as like steep and short wavelength, or is it going to start to mellow out and that energy is going to try to spread itself out? Mellow out. What do you call it when that big wave, maybe big, well in that example, louder?
Swell.
It's a swell. These things progress, and as they progress through deep water, they become swells. Okay. Everybody cool without me writing much more other than, hey, these things exist? Good with that? Okay. I want to knock out one more little part just so we have it, because there's some weird ideas in here. Yep. We're going to switch back and forth throughout, but that's the basic kind of overview of our deep water waves, at least for now. Okay, in contrast with that, you have deep water that's depth is what? With respect to a wave? How do you determine if water is deep from the point of view of a wave? It better be half the wavelength or greater than that. Okay, in contrast, rather than deep water waves, we get these shallow water waves. So shallow water. Now, things in our world, regardless of what it is, typically go from a continuum, with the exception of computers, it's not yes or no, right? There's middle ground between everything. Okay, same thing's going to happen here. If a wave is traveling through water that doesn't quite qualify as deep water, it doesn't automatically have to be shallow. There's middle ground, there's a continuum there. So shallow water is the other end of this spectrum. We're just going to say shallow water waves, rather. If we have a wave that we're going to say is a shallow water wave, it must be some sort of relationship between the wavelength and the depth. There's a lot of middle ground, as I mentioned, but we'll just say at basic, these guys travel in depths or in water whose depth, and we could do the same thing, we get a bunch of different answers. When I think shallow, just to share, anything that I would expect to see like a reef is what I would consider shallow. So 40 feet is pretty deep water for me, but if there's a reef 40 feet down, I'd still say it's a shallow reef, personally. Whether I'm right or wrong, I don't know, it's kind of subjective. Okay, in this one, the depth D has to be less than, so much smaller, 1/20th lambda. What was lambda? Wavelength. I will write the word, but I want to encourage you guys to... I'm already at something that I hate mathematically, but we're not in math class, so that's okay. Okay, so we're going to do the same thing real quick. We're going to switch this one around. I want you guys to think it out with one another. A shallow wave. Shallow wave has wavelength.
Is the wavelength supposed to be an exponent?
It is not. Does it look like an exponent?
Yeah.
Okay.
Just to me, but
I'm going to show you some of my crazy with math. I want everybody, real quick in your margin, draw me 1/5. Write 1/5 as a fraction. So, anyway, weird little sidestep. I say a shallow wave has wavelength equal to, I don't know, 37 feet. Okay, I want you to find the maximum depth. Max depth of water is the question. So that's kind of caveman-y written. That's my bad. If a shallow water wave exists in 37 feet, what is the max depth that we could still call it a shallow water wave? Talk it out with your neighbors. Little tiny bit of math. But discuss it. Get it. I think so, but I also haven't done it yet. But we'll do it right now. Check it out. The depth, D, we know it's less than 1/20th the what?
37.
Why 37?
Because that's the wavelength.
Indeed, it is, right? Okay. Now, 37 over 20 is kind of an ugly number. 37 over 2 is much less ugly, but I'm totally understanding that not everybody can do 37 over 2. That's what, 18.5? Okay. If you need a calculator, I'm going to move a decimal because I'm doing a bunch of it in my head. I don't have a calculator handy. Ask your calculator. There should be some in your desks. About 50% of you, I think if you pop open the desk, you'll see a calculator. Or people are stealing them everywhere. 1.85, Adam, is that what you got? Okay, so one little step of math, this is our answer. Kind of. Now, if I said, hey, what's the depth of the water this wave travels from? You say D is less than 1.85. That doesn't really do it, right? I'm not going to make you guys write them like this, but we need to make sure that anytime you're doing math with a real purpose, other than just math for the sake of math, the context is super important. What does this answer actually mean?
The depth could not be greater than 1.85 feet.
Yeah, this wave is traveling through water that's like this deep. That is super duper shallow water. It would not really have a wavelength of 37 feet. I just made up these numbers. The depth, and again, I'm not going to require that you guys do this because we're not going to have a bunch of math, but it seemed like a pretty natural spot to hit it. The depth is less than.
So, what changes, like, how will you know that it is, like, shallow water? Because with 37, if you said the wavelength is 37, then that's it. You don't say it is shallow, if that's the question.
You don't have to. You would not have to.
But then I could go, okay, let me figure out if this is deep or shallow, and I could use half of 37, and then just say, oh, this is how deep it is.
So,
And that's not true.
say that again.
Like maybe I'm missing something, but if you don't say in the question that it's shallow or deep, you just say there's a wavelength of 37 feet.
Mhm.
Is it deep or shallow?
So you would not be able to answer that question right away.
Right.
The only reason you were able to do this one is because I told you it was a shallow wave.
That's what I mean.
Yep,
Yeah.
yep. So that would be specified.
Okay.
And like again, not a
Because
math class.
I'm just thinking I can do half of 37 and then just say the, whatever it is, I forget.
Yeah, for
18.5.
18.5. But yeah. So what we're not seeing, and how many of you prefer decimals over fractions? Okay, you're wrong. You're not really wrong. Looking at this, notice if this is a decimal, this is 0.5, right? 0.05, I'm sorry. Okay, so when we're looking at this, just to try to connect that, notice there's a whole bunch of middle ground in here. Now, why we would even care about it, maybe that's a bigger driver of the question. If a wave is traveling and it's considered a deep water wave, its impact on the water below it, and in turn the marine life and the ecosystems below it, are different than the way that wave's going to act if it's a shallow water wave. So there are fundamental reasons. This sort of question, I promise, is not going to show up on a quiz. Only doing it because it seemed like a natural place just to talk about it and hit it to see if we can work with it. Okay, now as we go through here, what we wind up seeing is if we look at this transition area, there are some pretty big things that wind up happening as waves transition or progress, you might say, from being deep waves to shallow waves. Anybody ever been to the North Shore of the Big Island in Hawaii? I think I have too, but I'm not 100% sure. But I know what people do on the North Shore. They surf. Now, as you're looking at it, if you have a wave breaking on the beach, was it born and began on shallow water on the beach? No, waves don't start suddenly, right? They do, but they start in the middle of the ocean, they travel and they progress, yeah? So as we're looking at it, when we see these interactions happen, a really easy way to start looking and seeing this progression of changing or transitioning from deep to shallow, we're gonna look at one visual, and then I can already feel that I'm talking a lot and a little bit of glassy eyes going on. So we might transition rather than writing this. I want to transition to the book for a few minutes, and then we'll come back together as a whole at the end. Okay, so take a short break. If you need to go get a drink or use the restroom, now is your non-participation point opportunity to go and come back quickly. Mind, we're going to have very different language, just so you know. Literally, word for word, I have deep water well or deep swells, they're chilling. That's what I have. They're obviously progressing, right? They don't just chill unless it's really cold. But you have big swells running through the water, right? So that's what I see on the first, and I guess I can point to the picture here. We have some swells that are generated maybe by wind or a landslide eventually. Like, who knows? These are progressive waves that have become smoothed out, and now we're looking at some lovely swells. Okay, so at this point, we have nice swells, right? Nice, smooth, even wavelengths going along. And what we see a little bit here is, we talked about this yesterday, this is that orbital motion. We see the water is naturally folding in and over itself and is running a circular path. And the deeper you get or further away you get from the actual wave, the smaller that motion is. Eventually it's just gone. Like the bottom of the ocean 3 miles down isn't moving up and down with the waves 3 miles above it. There's just way too much stuff between them. Now, when we start getting and making this transition, deep water, deep water, deep water, and I'm not going to physically measure, but somewhere in here is where that transition between deep water and shallow water occurs. Okay, these waves, we're not adding or taking away any energy to them, but what we see is the energy is moving. What on earth is causing these large, smooth swells to start to bunch up here? So the earth itself, what do you mean by that?
It's like pushing closer. I don't know. That's what I'm thinking.
The surge?
Like it's getting closer to
So
the
that
land.
it has to do with the surge, absolutely. Okay, so check it out. If we are just walking, and here I am, I'm not really a wave, but it's just my hand, right? Right now, this part of my arm can move freely because it's not dragging or doing anything. This part of my arm can move freely, it's not dragging, it's just staying the same height, right? Now, I have to kind of fudge this a little bit, but let's say that I'm now at a depth where the bottom of this movement starts to touch a sand. And I think you said friction is what I think I heard, Adam. Perfect word, love it. Okay, if I start pushing and I'm good, and then my elbow touches, does that necessarily slow down the top of this hand? No, everything up here still moves the same speed, and we see these start to tip. When that happens, the bottom part of the wave slows down, the top part of the wave behind it didn't. These start naturally, just due to friction, getting closer and closer together. Eventually, if the conditions are right, those waves get so tall and heavy due to the friction at the bottom that what happens with the waves? They crash, they break. Now, the energy behind those, we get to experience probably more than most, definitely, I don't know about most. We get to experience the power of waves crashing here, even though we don't get really big waves here. Like, very seldomly do we get real big waves here. Yeah, that's very true. Go 5 miles that way, and that story's very different, for sure. But looking at this, we see just the generation between, or the transition from these deep water, nice smooth swells into these violent crashing things that literally shape coastlines all around our world. Okay, for that, my 3-step process, what I had, deep swells, chilling, cool. Shallow water causes friction, that's what I used. What's an elliptic path? An oval. Okay, so this circular motion gets squished down. Okay, we see the waves stack, and then we get this lovely surge and surf that generates. Okay, this is going to seem kind of related, obviously, because we're talking about waves. Have you guys ever discussed waves in a science class?
Yes.
Okay, what sort of waves did you talk about?
Maybe sound.
Sound waves, cool. And we might even discuss sound waves in here a little bit, I think. Do you ever talk about electromagnetic waves? Okay, so that's, say it again. Okay, yeah, physical sciences where you probably hit that. All right, now, I don't have a glass of water handy, but water does some weird things when you try to look through it, right? Why? Like if I have a cup of water and I put a straw in, from your perspective, it might look like that straw is literally cut in half and it does this. We've all hopefully seen that if you try to look at somebody outside of the water or vice versa. There's weird stuff that happens. What's happening?
Like the light is being moved by the water.
I like it. We're going to bounce off that. It's close. Okay. When I am looking at Caden right now, the light is traveling from him and it's coming into my eyes, right? Okay. There's nothing there that's different, right? It's the air it's passing through. Light travels at a constant speed in a vacuum. Okay, with light specifically, if I look at a cup of water, is air different than water? Yeah. Would we expect then that light behaves differently as it travels through air than it does with water? What you're seeing when you see that straw magically break in half, it's called refraction. And that's a really fancy word that apparently somebody might have known, but just wasn't confident. Is that true? Did one of you three say that or no? Okay, never mind. I misread. All right, so as we look at this word seems so scary when we talk about it. Light waves refract. Right now, can you guys hear me? Like, you can probably hear me really well. I'm kind of loud, I think, relatively. You guys can hear me right now, right? Okay, do me a favor, close your eyes. Wet willies for everybody. No, not really. Okay, keep them closed. I'm going to keep talking at you. I promise I'm not going to give anybody a wet willy. Can you still hear me all the same?
Yeah.
Okay. Can you tell what I'm doing right now? Okay. I spoke right at the wall. I just turned my face and I right away, right next to the wall. Now, the sounds to reach your ears, but it's obviously different, right? You can open them now. Please don't fall asleep. Cool. The waves of sound reacted differently because they had to pass against this and back. So they had to reflect, not refract. I don't have a new medium that these can pass through. But we're going to finish today with a short discussion, and hopefully an easy discussion, on the idea of refraction. Now, in general, we are obviously talking about oceanography stuff, and physical oceanography is what we're literally talking about right now. But refraction happens with water, it happens with light and radiation, it happens with sound. Anything that's transported via a wave is possibly going to be refracted. Now, when we talk about refraction, all that this means is it's when a wave bends as it moves through a different medium. Okay. Waves bend and act weird. I stopped being able to spell for a second. They bend and they move differently as they pass through a different medium. Now, those mediums, it depends on the context that we're looking at. If I tried to talk to you underwater, you can't hear me nicely just because of the way that our language typically works. However, can you still hear stuff underwater? Yeah. Absolutely. If you go underwater and make a high-pitched squeak, you can hear it from really far away. If I was above water and I made the same squeaky noise, you're going to have to be way closer because sound travels differently through water than it does with air. We are all aware of that fact. Okay. Similarly, you guys ever seen a prism hanging in somebody's window? They're not as popular anymore. Like a crystal that light shines through. And people hang them up because they do something pretty. What do they make rainbows, right? Now, the sunlight that I see just as I look outside, can you guys see the whole rainbow outside right now?
Yeah.
So, depending, maybe. I'm going to say no, literally you can't. But in essence, yes, I agree. Because they're all there, right? All those colors are right there right now. Okay, when you hang a crystal, specifically to make rainbows look pretty around your room, sunlight hits it. And crystals, they're just a nice cube. Is that true? Like a perfect cube. Is that the ones that hang up to make rainbows look like? They're cut, they're jagged, because when light hits that glass, it changes, right? It's now passing through that. And as it changes, depending on how far it has to travel through the glass, it either keeps adding energy or they combine and make larger or smaller waves. Okay, those waves in the sense of light just change of color. That's all that you're seeing. Different wavelengths are being created because they refract differently throughout that crystal. Same thing happens with water, and it turns out it can be kind of responsible for some of the really scary stuff that happens. Anybody ever gone to a beach that has big red signs with skull and crossbones that don't swim here? Yeah. JB, you're in California. Did you go to the beach? I don't know where in California you were. Okay. So that's way more specific. This is everybody. What are the big scary signs that say don't swim here, you will die? What are they warning you about? Waves.
Current, or the thing that'll pull you
Sharks,
up.
maybe. Current. Trying to think of the song. I can't get it in my head soon enough to do it. A riptide. What's a riptide? It literally rips you from the shore out to the ocean, which means if you're not a strong swimmer and you get pulled out to sea, peace out. Okay, as we're looking at those, it turns out that this idea of refraction and waves changing is responsible for our riptides. Now, correct me if I'm wrong. In the middle of the ocean, a wave travels through water. Okay. As it gets closer to shore, a wave travels through water. They're both traveling through water, but I'm going to claim refraction still occurs. Why? Talk it out. There's water and water in both situations, but even though that's true, the waves still refract. There's something different about it. The question at hand, and this is the last thing we're going to do today, what's different about the water in the middle of the ocean compared to the water near the coast? So definitely going to be a difference. Not what I'm looking for, but you're right. I agree with you. Ooh, the depth. The way that a wave acts in deep water, or a deep water wave, fundamentally different than the way that a wave acts and the water behaves in a shallow water wave. That change in depth, turns out, leads to a lot of refraction as we meet. Okay, tomorrow we'll continue and go to the hatchery because we do on Thursdays. Quick trip and lecture stuff tomorrow. For anybody and everybody, if it's a rude comment, please don't shout it out in front of everybody. But if there's something that you love, you hate, you want me to change, whatever, don't hesitate to come to me. It's like we're starting a new semester here because it feels different. Cool. Later, Raiders.